Hey everybody, Dr. A here, and in this video we're going to be providing some background information on hydrostatic loads. So let's go ahead and get started. As you can see, I already have a lot of this background information written out for you, so I'm going to kind of discuss it through, but please feel free to hit pause on the video and write all of this down so you have it in your own notes. So let's go ahead and get started. So hydrostatics deals with liquids at rest. So what do we mean by that? Well, you can have liquids at rest or liquids in motion. So we're specifically talking about liquids at rest that is not really flowing. So it might, the surface of a liquid might move around a little bit, but it's not actively flowing with any kind of significant velocity or acceleration. So when we have a liquid at rest, what we become interested in is what's called hydrostatic pressure or hydrostatic stress. And the way we compute that is we say sigma sub h, that's hydrostatic stress, is equal to gamma L, which is the unit weight of the liquid, times Z, which is depth. Okay, so let's define these and go ahead and write this out in your notes. Gamma L is the unit weight of liquid, which has units of force per cubic length. So for example, that would have units of like pounds per cubic foot, or we sometimes abbreviate that as PCF. And if you had SI units, you would be looking at newtons per cubic meter, okay? Now again, Z is the depth below the liquid surface, all right? So if you look closely, this is a linear function, okay? I have this sentence here. This is a linear function, and it has the form y equals mx. So here, x is your independent variable, and in our hydrostatic pressure relationship, z is the independent variable. M is the slope, and in our relationship, gamma L is the slope. And then the dependent variable y is represented by sigma sub h. So it's a basic linear equation. Now, it turns out as you go below the liquid surface, a distance z, the stress is equal in all directions at a given depth z. So let's take a look at this figure I have here, okay? Here I have this water table, okay? So this symbol right here, it's a little triangle with 3 lines underneath it. That represents the water level or the water surface in a body of water. And let's say I'm interested in a water particle here that's a depth z below that surface. Now, the hydrostatic pressure is going to be equal in all directions. That's why we have all these little vectors here at that depth z. And it's equal to that equation, sigma sub h equaling gamma liquid times z. So that's what the basic premise of hydrostatic stress is. Now, let's talk a little bit more about the unit weight of the liquid, okay? If you're in a situation where you don't directly have the unit weight of the liquid, but maybe you have its specific gravity, you can relate unit weight of a liquid to the unit weight of water by its specific gravity. So we'll make a note here. We're going to say the unit weight of the liquid, gamma L, is equal to GS gamma W, since the basic definition of specific gravity of liquids is the unit weight of the liquid divided by the unit weight of water. Now, the next question becomes, what is this unit weight of water? Well, it depends on the system, right? So in general, in structural engineering, we express the unit weight of water in English units as 62.4 PCF and in SI units as 9.81 kilonewtons per meter cubed. So is that it? Well, if you take a fluid mechanics or a hydraulics class, you'll also note that the viscosity and the temperature also come into play here. And depending on, viscosity, temperature, and elevation above sea level, these values are going to be a little different. You might have 62.35, depending on, how viscosity and temperature are affecting the water. But for the most part, for structural engineering purposes, these are the values we use, okay? Now, if we were to plot these, we're claiming they're linear functions, right? So if I were to plot this on a standard Cartesian axis, this is what I would have. I would have my independent variable axis, which is normally an x-axis, labeled as z, and my dependent variable axis, which is normally like a y-axis, is sigma sub h, and the slope is the unit weight of that liquid. Well, in engineering, especially all forms of civil engineering, when we're dealing with hydrostatic pressure, what we typically do is we draw the water surface like I'm doing over here. And again, this little triangle with 3 lines below it is the symbol for water level. And what we do is we draw our depth axis pointing down, and then we draw our pressure axis pointing to the right. And then we see this linear increase, okay? The reason why we express this graphically in this way very often in engineering is because typically we are interested in the lateral load effect on a container or a wall due to liquid, okay? And so what we can then do is write the following. Now we're actually going to write something down, okay? I'm going to say consider the wall retaining a liquid, okay? So let's say we have this wall here. Maybe it's a flood wall. And this is the ground surface. And let's say that it's holding back a liquid. Maybe it's water, but I'm just going to say gamma L because it could be any liquid, okay? And so let me draw my ground surface a little bit more level back here. Okay, so let's say that I want to look at the lateral load effect due to all of this liquid behind this wall. Well, the pressure is going to increase linearly, right? From the surface of the water down to the ground surface, okay? And so let's call this dimension right here H. And let's say that, this is our z-axis going down, okay? So you notice as we get deeper and deeper below the surface of the water, that pressure is increasing linearly. Now, again, what we're most interested in for the sake of structural wall design, or in the case of a flood wall design, what we're really interested in is the lateral pressure. So remember, hydrostatic pressure exerts an all-around pressure, but if we're interested in the lateral pressure, and we know it's all around, then what we can do is draw this pressure distribution as horizontal, because again, maybe we're only interested in the lateral pressure on the wall, okay? Now, what is this maximum value down here? Well, this is going to be sigma h equals gamma liquid times the full height h. Remember, z is a variable, so if I'm at this point, that's a z value, but all the way at the bottom of this wall, I'm at a z value of h, okay? Z equals h down here at the bottom, all right? Now, if I want the equivalent hydrostatic force per unit length of the wall, what would that look like? I'm going to say F sub h is going to be, what? 1/2 sigma sub h times capital H. What is that? Well, that's just the area of this triangle, okay? That gives me the equivalent point load due to that linearly distributed stress, all right? And so what would that look like? If I were to redraw this, let's draw this more like a free body diagram style. Let's say that that's H right there, okay? Again, free body diagram style. And how would this look? So this equivalent force is going to be right here, F sub h. And guess what distance that's going to be? Well, that's going to be a distance of h over 3, because that equivalent point load, F sub h, is located at the centroid of that load distribution. Now, what are the units of this F sub h? Well, you can track the units, okay? If you have stress multiplied by a length dimension, you're going to end up having units of force per length of the wall, okay? Now, where is that per length? Well, this would be the per unit length coming out of the screen at you, okay? So if I were to draw this in 3D, what would that look like? Okay, if I were to draw this same situation in 3D, I would sketch a wall that looks something like this. Okay. And its height is h. And so that uniform distributed load, F, is going to look kind of like this, acting on the back face of that wall, okay? And again, that's at a height h/3 above the base, okay? And so when we say force per length, it's per length of wall coming out of the screen at you, all right? So that's it. That's pretty much how it works. And again, if you've had a hydraulics course or a fluid mechanics course, this will be quite familiar to you. But in structural engineering, we have to know about this because hydrostatic forces act upon our structures that we design. So we need to know how to develop those forces. Okay, so hopefully you found this video helpful. If you did, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.